Okay, this is some more notes from section 5.1. And now we're going to do the same y equals x squared, except we're going to do the right rectangular approximation method, RAM. Same interval, 0 to 3, and 6 subintervals, and again it's x squared. So this was kind of my curve, and we're going, again, the scale's a little bit altered. 1, 2, 3, and this goes all the way up to 9. And now we're going to use the right endpoints. Let me write these in here. This is going to be 1/2, 3 halves, and 5 halves. 2.5 is 5 halves, and 3. So these would be the right end. We're going to use all the right endpoints now. Again, 6 subintervals. So each of these subintervals will be of length 1/2, which would be the base of my rectangles. Okay, make sure you're aware of that. I don't remember if I put I don't think I put these into the homework problems. I probably should have. So you keep in mind that you are dealing with the areas of rectangles. Okay. All right. And so the bases are all going to be 1/2, and then the heights are going to be given by the right endpoint. So not this, we're not going to use the 0 now. That is 0. But we're not going to use the 0, we're going to use 1/2, right endpoint. And we have 6 rectangles, so we're going to use 6 endpoints, or 6 heights. 1, 2, 3, 4, 5, 6. So now we are going to use the 3, but not the 0, because we're using the right endpoints for the heights of these rectangles. So again, the first rectangle, the base will be 1/2, and the height will be f of 1/2. The next rectangle, the height will be, or the base will be 1/2, and the height will be f of 1. Next one, the height will be 1/2, f of 3 halves. That's my third rectangle. My fourth rectangle, the height will be 1, and I'm sorry, the base will be 1/2, and the height will be f of 2, because I'm using the right endpoint. The fifth rectangle, the base again will be 1/2, and the height will be f of 5 halves. And then the sixth and last rectangle, the base will be 1/2, and the height will be f of 3. And again, as in the last one, I just factored out the 1/2. And these are the heights of my 6 rectangles. So 1/2, f of 1/2, f of 1, f of 3 halves, f of 2, f of 5 halves, f of 3. And remember, the function is just squaring them. So this makes it a little bit easier. So we have 1/2 squared is 1/4, 1 squared is 1, 3 halves squared is 9/4, 2 squared is 4, 5 halves squared is 25 over 4, and 3 squared is 9. And again, we all have the same common denominator, so we can have 1 plus 9 plus 25 is 35 fourths, and then 1 plus 4 plus 9 is 14. And again, I use the distributive property, so I had 1/2 times 35 over 4 plus 1/2 times 14, which is 35 over 8, and that was actually 7. And then I went to mixed numbers, so this became 4 3/8 plus 7 was 11 3/8, and then I changed that to a decimal. And this is what I got, and that's the number they got for the RAM on page 266. That's how they got that. Now again, remember we talked about this and we said the actual area under that curve was 9. We used 12 subintervals, and again, the more subintervals you're going to use, the closer you'll be to the actual value. And in example number 1, when we used the 12 subintervals, we got 8.98, so we were pretty close. So this is definitely an overestimate, and you could look at this and you could see I'm over the, here's the area of the curve, and I'm way over here. Here's the area of the curve. I got extra, a lot extra. So I'm getting all these extras because I'm using a right rectangular approximation, or RAM, and because the curve is concave up, these are going to be over approximations. Okay? All right, so that wasn't too bad. Hopefully that makes sense, and you need to kind of draw these sketches and figure these things out for yourself. But there's no real. I mean, we are calculating, and that's what we mean when we say calculus. Calculus does mean to calculate, but we aren't taking any derivatives or doing any limits or anything like that. So these are all just numerical methods. And we saw using 12 subintervals, we got a pretty good approximation when we used the midpoint method, and that's what we'll cover next.